Now we'll talk about hydrostatic forces in on an immersed surface. So what if you have an completely immersed surface? So let's say you have some liquid, let's say water, and then inside this liquid you have an immersed surface, which from the side looks like this. And if I take a front view or a normal view, then it probably has some sort of an arbitrary shape like this. Okay, I hope you understand the figure. So we have this immersed surface which has this arbitrary shape, which from the side looks like a thin sheet. It need not be thin. I mean, that's not necessarily required. So I would want to calculate the force acting on the surface. Okay, so based on the ideas we already have discussed, you have all the tools available to calculate it. Basically, you have to calculate the pressure on the surface and then calculate the force. Um, in this case, I'm interested in what's happening on the top surface. It could be the case that the surface when it was immersed, on the back side of it, you have let's say in submarine you basically have some sort of a vessel. So on the inside you'll want to have some pressure so that you can balance the outside force. It's like a thin shell, so you would want to create enough pressure in the inside so that the outside gets balanced, if at all you would want to have high pressure in the submarine. So anyway, so the job is to calculate the pressure on the surface of an immersed body. Now it's simple. You simply figure out what is the pressure field. So let's say there is a force acting because of pressure, and I'll draw it using a vector. And then as you go deep, as basically let's take an arbitrary point here. So this point has a height h. I'll call it h as a function of x and y. I'll tell you what x and y are, but basically h is uh, I mean, this is the height which will decide the hydrostatic pressure. Well, let's talk about x and y later. I'll tell you where the origin is. Anyways, so then as you go deeper, the height increases, and then hence the pressure increases, and hence the normal force because the pressure increases. So we'll have some sort of a distribution of pressure which looks like this. I mean, the force because of pressure. Okay, so the job is simply to integrate these forces. Now, if you do that, and in fact, let us see if I can show you the derivation. I would not want to do the derivation here. It's usual mathematics with some calculus in it. I hope my screen's visible.
Yes, sir.
Let's open it in a different software so I can comment on it. Yeah, this is better. Right, so you can see the figure, the same one that I've just drawn. So what we see here is this body. If we look in the plan view, that is this view, what we see is that the body has an arbitrary shape. So it will have a center of gravity, that is CG, and this CG is simply calculated. I mean, what I've done is I've given coordinates using xi and theta. Okay, so theta is the inclination of the body, and xi is the distance it has from, if I draw a straight line from here to the surface. Okay, so any point I take on the body will have some associated xi coordinate. And if I want to calculate the xi for the center of gravity, then you can use this area of, the definition of a centroid. Okay, so center of gravity is the same as centroid if your gravitational field is uniform. So on Earth's surface, the gravitational field is the same everywhere. If you're talking about a body immersed in water or something, then it's simply a centroid that is equal, that's the same as the center of gravity. So if you want to calculate the net force acting on the body, that is simply the integral of the pressure acting on a differential area element. So what I do is I take a small area element d gamma, and then I calculate the force on this, and then I integrate over the complete surface of the body. That's what integration is. And this again, now the pressure is what is a function of height here. So I can then do a couple of steps. I go from, I write the h, which decides what the hydrostatic pressure is, and then I replace that to a coordinate transformation in terms of xi and theta. And it helps us. And finally, what we get, and that's the interesting part here, is that the net force acting on the surface is simply the pressure on the center of gravity times the overall area of the surface. You don't even know what, you don't even need to know what the distribution of pressure is. All you need to find out is where is the center of gravity. And that, of course, you can easily find out given the geometry of the body. You find out the center of gravity, and then you calculate the pressure here. And that is again easy because for the center of gravity, you can calculate the height of the center of gravity from the surface of the liquid, and then simply multiply the hydrostatic pressure at hcg times the overall area of the surface. It's that easy. No need to integrate. I mean, when you integrate, ultimately this is what we get. It's a very important relation, a very powerful relation. So it's worth knowing it if you're working with hydrostatics. Is that clear? I'll go to our slide. I'll put that picture as well in the slide. I'll do a copy paste later and share with you. So what we see is that the force acting on the surface is simply the pressure acting on the center of gravity. Let's say this is your Cg times the overall surface area gamma. Right. So that's simple. Now let us say I wanted to apply an opposite force so that the body stays stationary. Let us say I wanted to keep this surface that I have here stationary. So all you have to do is you have to apply an equal and opposite force. But for that, I have to figure out where exactly do I apply. So for keeping a body stationary, in addition to force equilibrium, you also need a moment equilibrium. So the next step is to calculate at which point should we apply this PCG times gamma on the opposite side from this side, so that the body stays stationary. Now, if you were to see the distribution of forces like you have here, okay, that's the force distribution. So we can see that it's not a uniform force. Firstly, the force increases as you go towards the bottom side of the body. So what we effectively have a feel is that we'll have to apply the opposite force somewhere here. If I apply at the center of gravity, the body will rotate because the net force is at the, I mean, the net moment we have is because of a force which is concentrated towards the bottom part of the body. Okay, so the next part is to calculate the moment And so what we'll say is that, again, I'll go back to that derivation to save some time here. So next is moment equilibrium. Yes, the question is, where should we apply a force of Pcg times gamma on the opposite side to ensure that the net moment or the net torque is 0, or there's a moment equilibrium. Okay, so for that, again, it's straightforward. You say that let us apply it at a distance d, and then you balance things and figure out the value of the distance d. So in this case, we what we do is we use these coordinates where x and y are basically evaluated from the center of gravity. So we'll say that at center of gravity we have x equal to 0 and y equal to 0, and then we'll find out what are the x and y coordinates of the point where the force has to be applied to ensure a 0 moment or a 0 torque. Okay, so we say that let us say that we apply, and by the way, this point at which we apply the opposite force, it's called the center of pressure. The reason it's called center of pressure is because the pressure distribution results in a net concentrated force. So all this Pcg times gamma is a force which is basically concentrated somewhere here because of the distribution of pressure forces. So we call it the center of pressure. That's the effective point where the pressure force is acting on the body. Okay, so let's say the center of pressure coordinates are xcp and ycp. So the net moment because of the balancing force is this coordinate from the center of gravity. This is xcp I hat plus ycp j hat cross, so r cross p and r cross f, sorry, and the net force acting is pcg times gamma in the k hat direction. So the k hat is, so if you have x and y like this, from the right hand screw rule, k hat is in this direction, and that is where you're applying the opposing force. So when you proceed with these steps to calculate, I mean, of course, you have to balance this with the overall pressure forces. So then you have to do an integration, and then what you finally get is are the coordinates of xcp and are the coordinates xcp and ycp. You can do it yourself. I mean, there's nothing amazing here in terms of physics. And what we see here is that ycp is negative. So that basically tells us that the center of pressure is below the center of gravity, and which intuitively, which qualitatively also makes sense, because the pressure increases as you go down. So the effective center of pressure point has to be below the center of gravity. Cp would have been equal to center of gravity if the body would have been horizontal, if the pressure distribution was uniform everywhere. But that is not the case in this situation, because you have an angle of inclination theta. So the pressure increases as we go down. Is that clear? In our summary slide here, I can simply write that this force F equal to Pcg times gamma is concentrated on Cp, which is the center of pressure. It's a bit confusing because we calculate the F by taking the pressure on the center of gravity, but this force is concentrated on the center of pressure. But if you see the derivation, then this all makes sense. So it's worth going through the derivation once. It's very easy, just to make sure that in the future you never get confused while trying to remember these things. Okay, and this center of pressure is below the CG always. I say always because you have a body at an inclination. If it's horizontal, then it's equal to it, but that's not an interesting case anyways. Any questions on this? Okay, so for engineering calculations, these results are very useful. We don't need to go to the first principles and do an integral all the time. Although you can do that, I mean, that's not a problem. And in fact, if you revisit the subject after a long time, you would want to do the integral and derive the relations yourself and then get confidence. If you work in the shipping industry and you would have to do these calculations, it's worth doing it for the first time. So derivations are always helpful to give us confidence that we do understand the subject, although you may not remember the final results, but that's okay. You should understand and remember them right now in the class. That's very important. Right, so hydrostatic, the next topic is to calculate hydrostatic forces on curved surface without actually calculating it by evaluating or estimating integrals. So this is again using a smart use of physical ideas. So let's say we have a curved body which is immersed in a fluid, and this time the body is curved, not like the one we considered previously where it was at an angle theta. So it was a horizontal body last time, but this time it could be curved. Let's try it again. So how would you find out the net force acting on the top surface of the body? Again, it's easy. You calculate the pressure field, but remember the body is curved. Geometrically, it becomes very challenging to do the integral. If I give you an actual problem with the shape of the body, you'll simply give up because you don't want to do those hand calculations, which takes a lot of time. It's a bit boring. It takes a lot of time. But we don't need to do that. If I want to calculate the net force because of pressure acting on the top surface, and let's say we want to, the body is of an arbitrary shape. Okay, so if I see the shape of the body, then it basically has some shape like this. So how do we do that? So what we do is we use a rather smart idea that of course the pressure distribution on the top side of the body is the pressure because of the fluid on the top side of the body. So I take a hypothetical fluid volume which sort of coincides, one side of which coincides with the top surface of my curved body, and then the other two surfaces are normal to and perpendicular to gravity. So this one is along the gravity, and the top one is perpendicular to gravity. So I take this hypothetical fluid volume, and I can do that. Remember, it's like we did in mechanics earlier. You can take any body as your free body. So the system is under equilibrium. That means the net force and the net torque acting on the system is zero. So that means that the net force acting on this hypothetical thick blue liquid volume that I have taken is also zero. Right. Now on the right surface of the this fluid volume, you have forces acting. This liquid volume applies force on the curved surface, and the curved surface then applies forces on the liquid volume. Yeah, of course, when you go down, it increases. So it's something like this. So what this does is this basically results in an effective force which you can split into two components. One we call the force in the horizontal direction, the other we call the force in the vertical direction. So if I can find FH and FV, then my job's done. Now remember, this blue fluid volume is stationary, and the forces acting on this blue fluid volume, which I call my free body, if I actually draw it here, let's say I'm drawing a free body here. So the forces acting on it are, one of course is its weight, call it W1. So this is my body 1. So W1. The other forces which are acting are this FV, the vertical component. So these are the two forces acting in the y direction. In the x direction, or the horizontal direction, I have FH, that's acting because of the curved body, and the other force is the force because of the fluid on the left hand side of this body. Let's call this F left. So these are all the forces acting on this body. Is there anything else? In fact, there is one force acting called W2, because this surface was not, I mean, the top line, this top surface was not coinciding with the surface of water. So there is some water above it as well. In fact, I could have taken the body in such a way. So this is the top surface. So we'll call this as body 1 and this is body 2. So basically body 1, sorry, the other way around. This is body 1 and this is. So essentially in mechanics, you'll have forces of two types. One is body force, one is a surface force. So body forces are volume forces, like for example mg, which acts on the amount of material in it, amount of mass. And surface forces are forces which act on surfaces, which are dependent on how much of a surface is exposed. So this F horizontal is a surface force that's acting because of the curved surface, Newton's third law. So it's applying an opposite force to the curved surface of the liquid. The other surface force is F left, that is acting because of the fluid which is on the left hand side of this imaginary free body. Then you have FV, which is the again a surface force because of the curved body acting in the y direction upwards. Then you have W2, which again is a surface force because that's applied in the top surface because of the weight of the fluid above it. But that's okay. I mean, it's acting on a surface. It's a surface force. And then finally, you have W1, which is a body force because it acts on the mass of the liquid contained or the fluid contained in this imaginary volume. And now our job becomes much easier because we can simply see that FH, let's use a black color, FH is equal to F left, and F left is very easy to calculate. Remember, I mean, F left is simply the it's a vertical wall, and the pressure distribution is very easy to calculate because this is a flat surface as opposed to the curved surface where your integral would become very complicated. This F left can be evaluated simply. Let's come to the vertical forces, FV. So we know FV is equal to W1 plus W2. Now W1 and W2 are both easy to calculate. W2 is simply what you have is a rectangle or a cuboid, and W1 is again a volume. So evaluating volumes for curved surfaces is quite easy. You have done that in the first year mathematics. So you can do that and then calculate the net mass and for contained in volume 1 and hence the weight in volume 1. Okay, so this becomes M1 plus M2 times G. So when you solve problems, you will realize, I mean, I'll give you a problem where you'll have to do it both ways. One is to do it by calculating the pressure field on the curved surface and then integrating over the area of the curved surface. The other is to do it using this way, and this way will be much easier, but the answer will be the same for both situations. Any questions? Right. So next we have a topic which you are comfortable with. So let me ask you a question, a general question for you to think about. Is there any, I mean, buoyancy, you know, right? Buoyancy force, if you take any body and immerse it in a fluid, then the buoyancy force is a force which acts opposite to gravity, acting on the body that has been immersed. And this force is equal to the weight of the fluid displaced by the body. So if you take a wooden block and you submerge it in a liquid, then there's a force of buoyancy that acts on the wooden block, and this force is equal to m liquid times g. So if you make the block bigger, keeping the overall density of the wood, overall mass of the wood same, what you'll see is that the net force will start, the buoyancy force will start dominating, because there's an mg also acting, which is m wood times, or let's say m solid times g. Okay, so we know this force of buoyancy. Now, can somebody comment, just think, is there any relation between force of buoyancy and pressure? Think from a molecular perspective. Okay, now mg is something which acts because everybody, because of the universal law of gravitation, gmm by r square, and when you find out that, that basically becomes m solid times gravity. So so there are overall just four kind of forces. So which kind of force? And you know that normal force, when you put when you take a solid body and put it on a surface, it's basically these electrostatic forces, of electrostatic force of repulsion between the atoms when they try to come too close to each other, that results in a normal force from the surface. So where is this? What is the molecular origin of this buoyancy force? Now, earlier in the last lecture, remember we took a volume and we balanced the forces on it. So I told you there's only two kinds of forces. One is surface forces, the other is uh, body forces. So body forces are the ones which act on volumes, which is mg in this case, and then surface forces are the forces which act on the surfaces. So all the surfaces of this solid are being acted upon because of fluid pressure. So basically what we see is that buoyancy is not a new force. It is simply a way to understand the net force of pressure. It's a net surface force, net pressure force acting on the body, and that is called buoyancy. Okay, so you don't even need to use the word buoyancy anymore. If you say pressure forces, that by itself would mean a buoyancy force. Okay, for more detailed analysis, you will actually stop using the idea of buoyancy force. Okay, so let's see how is that force of buoyancy that we have learned about is exactly the same as the differential force on the body because of a pressure distribution, a pressure field distribution. So let me write no new force. So buoyancy is no new force. It is It's a net effect due to pressure gradient, the spatial pressure variation in the fluid. So let's do that. I mean, let's take this body that we have just taken. Let's draw it in 2 dimensions for simplicity. So we have this square body. In the 3rd dimension, it becomes a cube or a cuboid. Now this body is immersed, let's say, in a fluid. Now the fluid on the top surface is going to apply a force, and that will be equal to the pressure on the top surface times the area of the top surface. Now at the bottom surface, we'll experience a force because of the pressure of the fluid, and as we know that the pressure at the bottom surface is more, so that will be P top surface plus, let's say, the height of the body is H. So the pressure at the bottom is pressure P plus rho of liquid, okay, G H, and this multiplied by the area. Now since we have taken a cube or a cuboid, the areas at the top and bottom will be the same. Now of course there's going to be a force from the left and right directions as well, but from symmetry arguments they'll be equal. So I'll not consider these forces, I'll only consider the vertical difference in the forces. So now we can see that this the net difference in the pressure force on this body results in a top force which is equal to rho liquid G H times area. Now this area times H is simply the amount of liquid displaced. Now in this case this is equal to the volume of the body, solid body, but that is because the whole solid body is immersed. But for some reason, if let's say only half a body was immersed, the free surface of water would have started from here, then in that case this would have been pressure atmosphere, okay, and the pressure here would be P plus rho liquid G, and then it will be this height H, let's say partial, okay, because the pressure here is atmospheric as well. So basically this H times A that we have here is the volume of liquid displaced, and then you have rho of liquid. So if I multiply rho of liquid times the volume of liquid, it becomes the mass of liquid displaced times gravity, and this is acting upwards, and this is nothing but your force of buoyancy. Any questions? Many people have questions at this stage because it is questioning the earlier belief that buoyancy is actually a force. I mean, it is a force, but it's a result of a net pressure differential on the body. So, any questions? Feel free to answer, ask. Sorry. Right. So, no questions means everybody is happy. In case you have questions in the future, do feel free to discuss. Okay, there's a question by Shashwat. Will we consider the wood absorbing the liquid while calculation? No, in this case, we are assuming that the solid is non-permeable. Okay, so there is no absorption happening of absorption of liquid happening in the solid. If it does happen, then for a first level calculation, what we'll say is it will result in the overall mass of the solid being increased, or you can say that overall density of the effective solid being increased. But in this case, there is nothing like that being assumed. Well, if you have a thin sheet immersed, then of course H becomes almost zero, right? So the whole idea of thin means that H is tending to zero. So if H tends to zero, then there's no net differential, so there's no buoyancy. I mean, from your old ideas, you can also say that if you immersed a very thin sheet, then since it is a large area, but the volume is negligible, so it does not displace any significant volume of liquid. Hence, the force of buoyancy is zero. Now, the question that comes is, earlier you have learned that the force of buoyancy is simply the mass of liquid displaced times gravity. Nobody tells you if I take let's say a body like this, if I rotate it, now if I rotate the body, then right now the difference in the force acting is because of this height. Now if I rotate the body and the body is now lying like this, from your old ideas of buoyancy, and the amount of liquid displaced by the body is still the same because they're all fully immersed in both situations. Okay, so this is situation 1 and this is situation 2. So the force of buoyancy should be equal, but in this case now the pressure differential is happening over a height which is much larger. So how can they be the same? Okay, so this this is a question I'll ask you to figure out for an arbitrary shaped body. You have to think about it. Only then you will get confidence that yes, it is indeed the same force. So the question or the food for thought: why does force of buoyancy stay the same for a fully immersed solid even if we rotate it? Okay. Now, if you have an arbitrary shaped body, what you can do is you can take basically sort of these volume strips. Okay, and then you'll have a P here, and then you'll have let's say P1 here times this small area d gamma, and below you have P2 times d gamma. So the net df, I'll call it df because we're taking differential strips in the vertical direction, will simply be P2 minus P1 times d gamma, and this P2 minus P1 is simply because of rho g, rho liquid g, and then it's the height. So this will call dz, sorry, delta z times d gamma, and you have, this is your df vertical, and you have to integrate it over the complete body. Okay. So this, when you integrate, the total force in the vertical direction is integral of df vertical, which is rho liquid times g integral of delta z over d gamma. Okay. So d gamma was this top area and delta z is the length. So that will give you some sort of dv, and then you integrate, you get the volume of the complete solid body. Okay, so please use these ideas and try to answer this question. It's a very important question. One must be satisfied that this indeed is the case. Any questions? Right, what's the time? Right, so we are out of time now, so we'll stop here. There's only one problem I wanted to discuss, more as a tutorial discussion that we'll do tomorrow morning. Okay. So I'll stop the recording now. If anybody has a question, feel free to ask.